Okay, so class 9 science, TEST-12C, okay. Chapter 12 sound. Let's do the sums here. First go to question 8. Page on textbook page 196. 186 you'll find that, okay. Let me read the question for us. Listen to it carefully. Two children are at the opposite ends of an aluminium rod. Okay, there is an aluminium rod and one child is on one side, the other child is on the other end. Okay, one strikes the end of the rod with a stone. So one of the child strikes one end of the aluminium rod with a stone. That means sound is produced. Find the ratio of times taken by the sound wave that is produced by the striking in air and also in aluminium. So once the aluminium rod is struck, sound would be traveling both in the aluminium rod as well as in the ear. So we have to find the ratio of this time taken to travel by that sound in the rod. We have to find that ratio in the rod and the ear. Okay, how do we go about doing this? So as we read the question clearly we see, okay, but before that, from while doing the lesson inside the chapter, from table 12.1, table is like that. This you'll find textbook page 179. You may open your textbook and see there is a table, right? 12.1. There, sound, speed of sound in different medium is given, and from there we can find out the two that we need. Speed of sound given in this table in air, page 179, is given as 346 meter per second, and the speed of sound in aluminium, symbol for aluminium is AL, right? Capital A, small l. So 6,420 meter per second. So we see sound travels much faster through aluminium than air. Just a side information. Now let us assume here, let d, okay, small d, be the distance traveled by sound, b the distance traveled by this sound that is produced by striking the aluminium rod, distance traveled by sound in both air as well as aluminium. So you would imagine, suppose this is the aluminium rod, one child is here, the other child is here. Well, this child strikes this rod end part with a stone, I think, right? With a stone, yes. Then the sound that is produced will be traveling through this rod at this speed, and the same sound would also be traveling through the ear at this much slower speed. So the distance that the sound has to travel through aluminium and ear would be the same, right? Because the gap distance between these two child is the same, right? The aluminium is the gap between them. That's why we're putting d as the distance traveled by both air and aluminium to be same, which is d. This diagram is just for making us understand, okay? Otherwise it's not absolutely necessary for you to draw. Okay, so it's up to you if you want to draw. Now next, so let us just write down the required ratio. Find the ratio of this time taken. Let me read the exact question. Find the ratio of the time taken by sound wave in air and in aluminium to reach the second child. So to reach sound time taken by the sound to reach first child to the second child, how much time? Ratio of the time taken in air and aluminium. First is in air and aluminium. So the air is mentioned first, means on the numerator. The ratio means comparison by dividing. Time taken Okay, by sound wave, according to the language text, by the sound wave, to travel in air. Just keep it simple and listen carefully. I think that's all that we need to understand. Divided by time taken by the same sound wave to travel. Okay, let me add something here. Travel in air, to travel in aluminum. So that is what we're trying to find out. So let us do this. So that will be equal to, now we know the formula for speed is equal to distance by time. So if you bring this time up, it will go to numerator and multiply with the speed. So time formula will be distance divided by speed. So we're going to use this. Time taken, distance by speed. So time taken, distance is the same in both the cases. So let us write down here. Maybe we may rather continue here. So distance is same by speed for air, to travel in air. This is the speed from the table. So 346 meter per second. Next, time taken by the sound to travel in aluminum will be distance to be traveled by the sound wave in aluminum divided by the speed of the sound in aluminum. This is 6420 meter per second. So it's a matter of just calculating carefully. So write this one down, d by 346 meter per second. Then if we change this long line, which is divided by, into multiplication sign like this, then denominator will go up. We create some space here on the right side. D by 346 meter per second into then 6420 meter per second divided by this. Denominator will go up, numerator will come down. So d and d cancel. Meter per second cancel. Then we can cancel this with 3 is going, I think. Is that 3? It was a 3. Oh, so let us just do this one. 2 is going, I think. So clearly 2 is going. 2 1s are 2 1 in hand. 2 7s are 14. 2 3s are 6 then. 2 3s are 6. 2 2s are 4. 2 1s are 2. 0s are 0. So we're going to get here the ratio as 3210 divided by 173. So let us write it in the form of the textbook answer, which is they have divided into the decimal form. So let us divide this number. 3210 is divided by 173. So let us try with 1, then 173, because 173 into 2 will be too much higher than 321. 11 minus 3 is 8. 1 taken, so 11 minus 7 is 4. 2 minus 1 is 1, so 0. Let's try with 8. 8 3 is 24. 58. It's going. So 10 minus 4, 6. 1 taken, so 70 minus 8, 9. So next point, then 1 will come here. Okay, so let's try with this space. 5 will go, I think. 5 3s are 15. 5 7s are 35, 36. 5 1s are 5, 8. 5 remain. Then 1 is taken from here, so 15 minus 6, 9. Again 5 will go, so 865 again. 5, then here 1, 14 minus 6, 8. So 4 will go. 4 3s are 12. Okay, 4 3s are 12. Then 4 7s are 28, 29. 4 1s are 4, 5, 6. So since we have reached the third place of decimal, on the right of point are called decimal places. You can stop there. So our answer here will be equal to, when these two are divided, 18.554. So this is the ratio, and we can finally write it as 18 point. Third place of decimal is 5 or less than 5, then less than 5, which is 4, then the preceding second digit will remain same. So the required ratio is approximately 18.55, like exactly like the textbook answer. Okay, now 18 is done. Sorry, this is not 18, this is 8. Sorry, question number 8. Next, 9 will go. Question number 9. I hope you're getting it right. These are the basic formulas we're going to use in this chapter. Okay, so I just wrote it down by the side. You will remember we did these 3 formulas in the first class, first test. So 9, let me read for us. The frequency of sound is 100 hertz. How many times does it vibrate in a minute? So here, as we read the question is saying frequency, and we have decided frequency will be small v, is 100 hertz. The language of the text here means, question says this means, we know in our chapter we have studied, frequency is a certain number, means frequency in simply the number of vibrations in 1 second. So in 1 second time, this sound means it vibrates, it means the sound it vibrates, equal to 100 times. Frequency is 100 hertz, means frequency definition is number of times a sound wave vibrates in 1 second. So in language form we can put in 1 second this sound of 100 hertz is vibrating 100 times. That's the meaning of 100 hertz frequency. 200 means it is vibrating 200 times in 1 second. Number of times a sound vibrates in 1 second is called its frequency. Okay, we have learned this in the main chapter. So in 1 minute, question, go back to question. How many times does it vibrate in a minute? In a minute means 1 minute. In 1 minute there is, 1 minute contains 60 seconds. So 1 minute or 60 seconds. In 1 minute or 60 seconds, it vibrates how much? The question is asking. It vibrates equal to, okay, let us just do some analogy here. Just like 1 mango is costing you rupees 20, then if you were to buy 60 mangoes, how much? 10 mangoes, how much would be the cost? Common sense. 1 mango 20 means 10 mangoes. Yes, 200. How do you get that? Price of 1 mango, which is 20 rupees, multiplied to the number of mangoes you're buying, then you're gonna get the 200. Similarly, 1 second, 100 times it vibrates. So 60 seconds, it will vibrate. These two will multiply 160, just like 20 and 10 mangoes are multiplied. So you're going to get 100 into 60 times it's going to vibrate. Just comparing a simple calculation that we easily do with the one we're doing here, and I think you pick right. So that will be equal to 6,000 times. So this sound will be vibrating 6,000 times in 1 minute. That's your answer. Okay, 2 more questions are there. I think we can do this in this class itself. Simple, okay, if you listen carefully, that's all. So here 13, question number 13, page 186. Let me read it once. A stone is dropped from the top of a tower which is 500 meter high. So let us say this is the tower which is 500 meter high. This stone is being dropped, means in a downward direction, into a pond. So this is the pond, P-O-N-D, water pond. At the base of the tower, means at the bottom of the tower here, the pond is there. When is the splash. So when the stone hits the water in the pond, there will be a splash sound, right? That sound, when is the splash sound going to be heard at the top? Means how much time it will take for the starting from releasing the stone and producing the sound, and the sound to reach back to you who is dropping the stone. How much time will you take to hear if you were to drop it from a 500-meter high tower? That's what the question is saying. So clearly, as we read the question, we find that here in the motion chapter we're using s as a distance, so f is equal to 100 meter. According to the language of the text is height of the tower, right? Keep it simple, okay? And then as you read the question, g is given as we have to use 10 meter per second square. This is acceleration due to gravity. Look into your text and you will see this is the given value there. When the plus and in the bracket, given g is 10 meter per second square and speed of sound 340 meter per second. So if acceleration is 10 meter per second square, acceleration due to gravity, then acceleration of the actual stone you are dropping is denoted by a, and since it is in the downward direction, it will be plus. It is in the same direction as gravity, that's why plus. If you are throwing the stone up, a would have been opposite to the direction of gravity, so it would have been minus. But for any object that is dropped, it is moving in the same direction of gravity, so it's plus. We know this, right? In the chapter motion, first chapter of physics, chapter 7, we did that. So this is nothing but, this is acceleration of the stone. And we may write here, why we put plus here is because downward fall. This object stone is experiencing downward fall. If it was thrown upwards, it would have been minus. We know this very well by now, right? So a is also there. Then we know that for any object drop, just before you drop, we all agree it is stationary, not moving. That means not moving means initial velocity. Initially, before the stone is dropped, initial velocity, any object that is dropped is always 0 meter per second. This is the initial velocity of the stone. For any object that is thrown up, when it reaches the highest point, it stops. So final velocity is v is 0. But for an object drop, initial velocity is always not moving initially, so u is 0. But for an object thrown up, finally it stopped at the highest point. So stop means 0. So finally stop means final velocity is 0. We know that by now, right? So u is 0 because it's an object that is dropped downwards. Now we'll do well to remember the three famous motion equation, that is for uniformly accelerated. Of course, the object has to be in uniform acceleration. So v is equal to u plus at. The first formula, very well versed by now, I think. 2as is v square minus u square, and the third formula is s is equal to ut plus half at square. These are the three famous equations of motion of a uniformly accelerated object, right? So which formula is going to apply? We want to find the t here. So t is question mark, time taken for the stone to reach the pond. Okay, 500 meter to travel 500 meters. This is the time taken for stone. That is what we want to find, taken for the stone to reach the pond. So among the three, let us choose which is going to fit our purpose to find t. S-A-U-T is there. S-A-U-T. The third is the one where time is given and that follows, that matches our situation. The first one also has t, but we don't have the information for v, so we can't use. But here S-U-T-A-T, A is there, S-T, U is there, so third one is the appropriate one. So we may as well write, since by formula S is equal to ut plus half at square, so that will be equal to u is here 0, so 0 meter per second, because if we bring this second to the power minus 1 to the denominator, it will become plus 1. We're doing that to cancel out the s. Okay, so here t, the time, or before that, I think let us just change this in the format where we can directly find out this one, t. So s is equal to here, or we can just put it and solve it like the way I did just now. This also okay, 500 meter. Okay, let's just start putting the values, and then u is, we need some space though, so let us just use the space here. Okay, I think it should be okay. We'll remember this too, and then let's just do this. So here, let's just write down that implies 500 meter for this s is equal to u is 0 meter per second into t. We don't know yet, just put it there, half into acceleration here, 10. So 10 meter per second square. This minus 2 come down, then plus 2, power will become plus 2 into t square. So just keep it like that, t square. Okay, so once we're through with that, it's better to do this way, because this 0 will cancel out this t. 0 multiplied to anything is 0 into t is 0. This whole thing will become 0 and disappear. So we're going to get here 500 meter is equal to, and then we can cancel out this one, I think. 2 1s are 2, 2 5s are 10. Okay, so we're going to get a situation where this is 5 meter. Okay, 5 meter per second square. You can bring it up again, I think that's fine, into t square. So next step here, you may keep this t square on one side, then 500 meter divided by this will come down, numerator will come down if you shift to the left side, meter per second square. So this meter will cancel, 5 into 100 is 500. So having done that, coming from here, okay, from here to here, and then we're going here from here to here. So that'll give you t will be equal to, we may as well write this one here, t, then you remove the square, then the root will come 100, then this second to the power minus 2, bring it up, then it will become second to the power plus 2. From denominator, if this is brought up to the numerator, you know this minus 2 power will become plus 2. So there will be 10 into 10 is 100. So 10, 1 will come out the square root, and second to the power 2 becomes second to the power 1. So t is 10 seconds, meaning it will take 10 seconds for the stone to reach from here to the pond. But the question is saying how long will that sound take to reach you again. So after the splash, the sound for the time taken for the stone to fall to the pond, that is 10 seconds. From the pond, the splash sound to reach you, that is another time we have to calculate. So let us go about doing that now. So this is done. Time taken for the stone to reach the pond, 10 seconds, done. Next, for the sound. So we have to calculate for the sound. After the sound is produced, the sound has to travel up again to you. So for that, let's do here s. So s will be 500 meter again. This is the distance that the sound must travel to reach the top. Distance the sound must travel to reach the top. The distance for the stone to travel from here to the pond is 500. For the sound to travel from the pond to you, it's also 500, as same. Then Vs, let us say, Vs is equal to 340 meter per second. This is given in the question. Look there into the question. There, right? This is the speed of the sound given in the question. Speed of the splash sound to travel. Then having done that, we have here, there's the TS, question mark, is the time taken for the sound to reach the top. Time taken for the sound to reach the top. Okay, to reach the top. Okay, after the splash is produced. After the splash is produced. I hope you're getting it right. After the sound produced, the sound to reach the top. This is the TS. T is the time taken by the stone to fall from top to the pond before the sound is produced. TS is the time taken for the sound to reach the top after the splash is produced. Okay. Now this is quite simple since we know, okay, the formula for time is equal to distance divided by speed. This is the general formula. From this formula, speed is equal to distance by time. So time, if you shift here, distance by speed. We are doing that. Okay, the basic formula. So having done that, we may move here and write down that will be equal to distance is S. The distance for the splash to travel to the top, S. By speed is the speed of sound here, Vs. So this is the distance by speed of the sound. So distance to travel is 500 meter by speed is 340 meter per second. 340 meter per second. As you can see here, that is meter cancel, 0 0 cancel. Then this 2 1 2 7 2 2 25 by 17. So if you divide that, you're going to get here this 25 divided by 17, sorry, 17 ones are 17. Then 15 minus 7 is 8.0. Okay, then you're going to get here, I think 4 will go, 4 was 7 are 28, 4 ones are 4 5 6, 2 and 1 and 0 again. Okay, so here 7 is going on, not 7 7s are 49, 7 1s are 7, 8 9 10 11, yes, going. Then here 1 remainder, 0. 10 after putting point 0 here, still not going, so 0 and 0. So we have reached third place, so we can just write down is equal to 1.470 seconds. 25 divided by 17, which is nothing but, we can come from here, final answer is going to come out. So that will be equal to 1.47 seconds, because third place is less than 5. Let's put this one as question number 2. For final answer, therefore, according to the language of the text, time taken for the splash to be heard. Listen carefully. Time taken for the splash to be heard. Okay, to be heard. This is what the question is asking. Time taken for the splash to be heard will be time taken by the stone to fall from top to the pond, which is here, T, plus after the splash is produced, the splash has to travel to the top again, that is TS, right, TS. So that is your answer. T is the time for the stone to fall to the pond, TS is the time for the splash to reach back to you. These two together is the total time taken by for you to hear the splash. So this is in equation 1, 10 seconds. In equation 2, this is, let us put it as equation 2 here, 1.47 seconds. So this is 11.47 when you add this to total time taken for you to hear the splash from at the top. For the splash to be heard at the top is 11.47 seconds. So that is your question number 13. One more question is there. I think we can just complete it up here. 14. Okay. I hope that's fine. Yeah, so let us do that. Here Question number 14. Let me read the question. Sound wave travel at 339 meter per second. If its wavelength is 1.5, so we can just start writing here as we read the question. Okay, so or let us just do this in the next class.